Exponential decay often has one other issue that sometimes students need to deal with that they sometimes overlook and don't deal with properly. End up making a very common mistake which throws everything off. That's why it becomes important for you to look at the feasibility of your answers, because if you don't put the right values in, you'll get a situation like here. You're asked how long will it take for a sample of plutonium 239 to lose 5/6 of its present amount, and so we're losing 5/6. As you can see down there, we also have plutonium 239's half-life of being 24,110 years. And what sometimes students do, and they misinterpret this problem, and what they end up doing is, they make, at least to me, if they do everything else right, they make a common mistake, and then they end up with an answer that's less than the 24,110 years, which would be the half-life. Now, you have to remember, a half-life is the amount of time it takes for a radioactive substance like this to lose half of its mass. So, there's no way it should take less time to lose 5/6 of its mass than it is to lose half of its mass. So, that's where sometimes students, overlook little things like that. And if you actually look over your answer and see how feasible it is with respect to the situation you were presented with, you'd have a chance to see that, well, in fact, that, this isn't, a correct answer. The formula we use, that P equals P sub 0 a to the T power, deals with the amounts that are present. Okay, so first I'm going to start with the half-life. I'm going to use the half-life to figure out what the value for little a is. So this should happen regardless. I mean, you should do this regardless of what's going on here. So, it takes 24,110 years, so I substitute that in for t, to become half the original amount. So the final amount is now half the original amount. When I work through the algebra to figure out what a is, I divide both sides by p sub 0, so they just cancel. That's why, again, I don't really necessarily have to have the starting amount. I then have to basically take the 24,110th root of a half, or basically raise 1/2 to the 1 over 24,110 power. So whichever way you choose to handle it. I mean, calculators can handle either way and give you the same answer. It's just like some students are not used to looking at a 24,110th root. But you end up getting a to equal 0.999971251. Now, another issue that often comes up with radioactive decay, and I mentioned this before, a should be less than 1. And it's certainly not going to be a negative value. It should be more than 0, but it should be less than 1 to indicate there's a decay. And most of the time, if you've noticed in the few problems we've done so far, I've typically rounded to 4 decimal places. Here I'm going to round to more, or keep more of the decimal places, simply because of the fact that if I round to 4 decimal places, a would be 1, and I wouldn't be able to go anywhere with that, because 1 to any power would be 1. I mean, so I have to make sure I'm still keeping some sort of decimal answer, and making sure I'm keeping enough decimal points that it doesn't want to round to 1 on its own either. Um, so I end up keeping a lot more decimal points for this one. Matter of fact, I keep all of them. So that's my formula for what's going on here. Now here comes the key factor again, always remembering that this formula deals with the amount we have, not the amount that we've changed by, or in this case, the amount that we lost. Because if we lose 5/6, a big mistake the students will make is they'll let P become 5/6 P sub 0. Well, you're dealing with the amount that you lost, okay? And that's going to affect things. I mean, so what you have to kind of do is, like, figure out what's going on with that. But this formula should be dealing with the amounts present. So that's why I'm going to make, P on the left hand side 1/6 of P0, because if I lost 5/6, I have 1/6 left. We're looking for how many years, so that's the T. So, so that's why I set it up this way. So that's a very key point, is that we lost 5/6, but in the formula, in the problem, we're going to write 1/6, because that's the amount we would have left. And I go through the same procedure. I divide both sides by P sub 0. I end up with this exponential. I'm going to write a similar logarithmic statement. So now another way of handling it, and because we have those logarithmic properties we have brought up before, primarily the power property, I can just take a log base 10 of both sides, just log. And that t would be brought down from an exponent to be a multiplication, so I would have t times the log of that 0.9997125 equaling the log of 1/6. And that would divide both sides by the log of 0.999.712 or 0.9999725 and get approximately 62,323.45 years, which seems to be pretty feasible. It is definitely over the amount of time it took for half of it to go away, from 5/6 of it to go away. So at least it's feasible from that end. I might want to check, make sure all the calculations are correct, run it through again, but generally, that's what the answer is going to be. That's how long it would take.